Hi, it's Todd. I want to show you how to program. Okay, look at this. Fibonacci sequence, easy. You can find this problem anywhere, on Google, whatever. So, the nth number in the Fibonacci sequence is the sum of the previous two numbers. And the first two numbers are 0 and 1. That's the Fibonacci sequence. So, write a function that gives the n number in the Fibonacci sequence given a positive integer n. All right, how would we do this on paper? How do we solve this problem if it was given on as a math test or something? So now look, what we do is we got to dissect this problem, okay? What do we got? The information, the first two numbers are 0 and 1. So we write 0, right? Write 0, 0. And then we write 1, 1. And then, so what's next? Well, we got this information, this data, right? Now, this information right here, the nth number in the Fibonacci sequence equals the sum of the previous two numbers. So now we're on the third one. Previous two numbers, 0 and 1. So add previous 2, 0 plus 1 equals 1. And then add 1 plus 1 equals 2. And then add, and then 2 plus 1 is 3. And then 5. And then 8, right? And then on and on and on. So now, how are we going to write this in a way that a computer can understand? Let's just consider this first. Before we do that, let's double check our work. 0, 1, 2, 3, 5, 8. Now, does this process account for positive integer n's? Anything greater than 0? What about 1,000? Yeah, it does, right? So we can just keep adding. 1,000 is going to be 199 ninth Fibonacci number minus 998, right? So yeah, it does. So let's do this. What are we doing here? We write 0. Let's say num1 equals 0, right? And then we write 1. Num2 equals 1. And then we add the previous two, right? Num3 equals num1 plus num2. And then num4 equals num2 plus num3, right? Okay, now look at this. Right here is basically what we're doing here. But we got to do this on and on and on, right? Now, these, we need to do this in a loop. Basic construct. What control structures do we have? What data structures do we have? We got numbers, we got integers, that's what we're using. And we also got loops as a control structure. So we're counting up to n from what? From 2, right? Because this is the second number. So we say, let's just, for now, let's just write this in a way that is simple. How do we write this? Abstract it into one formula. Well, we can say fib of n equals fib of n minus 1 plus fib of n minus 2, right? Those are the previous numbers, right? Okay, so how do we make this program work? Okay, what we do now, let's just test it out. What we're going to do here is called red-green refactor. Okay, we got this cool thing called PyTest, which allows us to test our Python modules here. So we got this file with a bunch of test cases. 1, 2, 3, 4, 5, 6. And this is easy, man. Woman, we just let the computer help us do the work. Test-driven development, write the test first, and then we write the code and make it pass. So red-green refactor. We ran the test. We got an error. Can't assign a function call. Okay. Let's just right here. Can't assign a function call. Fib of n. Oh, okay. Fib of n equals fib of n minus 1 plus fib of n. Hold on. N minus 2. Look at that. We made an error here. And then let's just comment this out for now. Okay. Okay, all failed. So let's get the first one passing. Then we'll get the second one passing, the third one passing. That's red-green refactor. So how do we get the first one passing? First case, we want fib of 1 to equal 0. Num1, return that. So let's say return num1, right? So let's get the first test to pass. It passed, yeah. All right, let's get the second one to pass. Fib of 2, we want it to equal 1. Num2, right? So now we want a branch, right? We say if n equals 1, then return num1. And then num1 we can just put up here, right? Now we just changed this. Now we want to make sure that our thing still pass, which obviously it does, right? Num1, so now here is a good practice, generally speaking, is to account for all logic branches. So if you have an if statement, put an else here, right? Now, some people disagree. Well, I disagree with them, okay? Now, we want to do the case where fib of 2, n equals 2. So let's insert elif n equals 2, then we return num2, right? Return num2. And then we can define this up here, right? Let's try this. Let's try to get this to pass. Oh, okay, there's an error. It's expected something in this indented block. Let's just put here for now, temporary. Okay, so we got more tests passing. Now, next test is fib of 4, and it's returning 1. Let's go through this. If n equals 1, no. 2, no. Else, yes. It does everything else. Returns 1, which is num2, makes sense. But now, here, this is where we want this to happen, right? So look at this. Remember it was giving an error before? Fib of n equals fib of n minus 1 plus fib of n. Well, fib of n is what we're looking for, right? So let's just say return this instead, right? So now we've got this branches, all of these cases are considered, right? And then we got this written out. Let's see how this works. That's how we do it, okay? We broke down the problem. We identified what we have, what we can work with, what we need. We wrote it out, how we would do it manually. And then, oh, my stomach's grumbling. Now, we write tests, and then we make those tests pass. Okay, one by one. Simple, right? Think of the data. Now look at this. Let's make this better. See, this is recursion. An easy way you can think about recursion is, well, first of all, it made it easy to write the program because we just literally wrote it in one line. Like, it makes sense, right? Fib of n minus 1, fib of n minus 2. Well, think of it like if you want a green dog, then what would you do? If green dogs don't exist, you buy green dogs and you breed them. And then, well, you buy dogs like a golden retriever that looks, yellow's kind of green, right? You're trying to find green, and you pick the greenest of the babies, the puppies, and when they grow up, then you mate those. And then the greenest of those, you mate those. So you do the same thing again and again and again inside of itself. That's recursion right here. Recursion, but it's really slow, okay? Because, see, the space complexity is on the order of 2 to the n. And I'll make another video about all that stuff, okay? But it's really slow. So what we want to do, and same with the recursion. Recursion is just generally slow. What we want to do is break this up to make it iterative. So how do we do that? Well, think of this. What is the data, like we did before, what is the data that we have that we need to find what we're returning? Well, we're finding the current, right? And then it equals the previous plus the previous, okay? And then what happens here? Let's write the formula for fib of n plus 1. It's going to equal fib of n plus fib of n minus 1, right? And you see we're breaking this down also, where we're writing out explicitly. And it helps us because we know now that previous becomes previous, and previous becomes current, right? See how they change on every iteration of a loop? We're going to have to loop through this, right? Because we're counting. That's iterative. Loops are iterative to version of the recursion, right? A lot of problems have both types of solutions. So now we say previous equals previous, and previous equals current, and let's delete that and return current. But we want all of this in a loop, right? For I in range 2 to n, count up here, okay? So now let's test this. All right, we got an error, unbound local variable, reference before assignment. We need to assign previous, and previous. Now we can put it above the loop. That would be the first step. But you know what? That would be redundant. We can just skip that step and do previous equals 0, right? And then previous equals 1. And try it yourself if you don't understand. Try putting it above the loop first, and then see that this is redundant, and we can do this right here. Oh, shoot. Now, it passed. Look at that. Okay, easy, right? Easy. We figured it out the same way that you build generally all software. You plan it out, you identify the problem, you analyze, and then you plan, and then you develop it iteratively. And we use computers where we can. To automate the things that are good to automate, that are worth automating.